Okay, so now we get to talk about that most devilish of fiends, carboxylic acids. Alright, the carboxylic acids really are the highest priority thing we're going to deal with, but I'm introducing them first before we get to the esters and the amides, because the esters and the amides are both derivatives of the carboxylic acids. At least structurally, they look like derivatives. Okay, so the structure of the carboxylic acids are fairly straightforward. You have your alkyl chain, and then you have this big group right here. Okay, so that's your carboxylic acid. You have your carbon double bonded to an oxygen, and it has a hydroxy group. Remember how I said, when looking at the aldehydes and ketones, you needed to be careful? Well, here you go. So, this whole thing is your carboxylic acid. If you don't have all of those, then it's going to be something else. So sometimes it's written RCOOH, if it's just being typed out. So you'll often see that COOH represented as your carboxylic acid, as the acid group tacked onto the end there. And thus, when it loses that acidic proton, it would be COO minus. But it's not always written that way. You can get carboxylic acids written in other forms. For example, acetic acid, HC2H3O2, is very common. Even though structurally it's H3CCOOH. The reason they would do it that way is because it's nice and compact, while still, pulling out your acidic proton for, special status. Now, really quick, the reason they're acidic is because of resonance. Okay, you remember resonance. Okay, so, say you have this guy right here, your deprotonated carboxylic acid. Now you have two oxygens and a whole bunch of electrons, and there's nothing to distinguish those two oxygens. So what can happen is, one pair of electrons can come down off of this guy, boop, flip down in there, thus forcing a pair of electrons off of that double bond, giving you, the exactly analogous situation down here. So really, you don't have either one of these pictures separately. Instead, you have the resonance structure, where that pair of electrons lives constantly partway in between, and each oxygen also has sort of temporarily half the time a non-bonding pair. So resonance makes this whole negative ion much more stable, which is why you get that acidic proton. Where normally an alcohol group, a hydroxy group, that proton is not acidic. Okay? But with the carboxylic acid it is, because of resonance. Okay, so how do we name our carboxylic acids? Well, like I said, these are going to have the highest priority. So as a suffix group, it's going to be oic acid. Okay. So notice that there is a space there. Okay. So acetic acid obviously is going to be an outlier. Common names are going to show up all the time. But what acetic acid should be is F, because there's two carbons, 1, 2, N, because there's no double bonds, oic acid. So it should be ethanoic acid, but we call it acetic acid. Similarly, you can get this guy. Okay. 1 carbon, so it's meth. No double bonds, of course. So N-oic acid. Okay. So, like I've said, these two have common names. This one here is acetic acid, as I've said before, or vinegar. This one, I don't know if you've encountered before, is formic acid. So named because it is responsible for giving ant bites their sting, and in French, ants are fourmis. There's no U in that, I don't think. Oh, actually, no, I don't know. I'd have to actually look it up. I know that's French for ant. I just don't know how it's spelled. Okay, that's also where we get formaldehyde. This is just as we also get acetaldehyde and acetone. That gives us formaldehyde from formic acid. Speaking of common names, we also get this guy that you're going to need to know. Yep, benzene always has a common name. But this one is nice and simple. Oops. Benzoic acid. Isn't that nice? You have encountered benzoic acid before, or at least you've encountered its conjugate base. Specifically in the form of Na+, sodium benzoate. That is a common preservative. You look on the back of any can of soda and you're likely to see sodium benzoate. Okay, so just the real important point here, oic acid. Oic acid. And if it has a, well, if it, just can't have the whatchamathing, the who's it, the what's it, if it doesn't have priority, then it is a suffix group, and a prefix. If it's a prefix, it is a carboxy. Okay. So we have oxy alkoxy. If we have an ether, it's carboxy, or oxo if it is going to be an aldehyde or a ketone as a prefix group. And now we have carboxy if it is a carboxylic acid as a prefix group, or if it's on a side chain or something like that. Now, because of their construction, the COOH, that uses up 3 of carbon's 4 bonds. So that carbon can only have one more bond. So you would think that these guys can only show up at the ends of a chain. And you would be largely correct if this were a sensible world. Okay. So you would expect that, something like this, where you have 1, 2, 3, 4 carbons, you would expect butandioic acid would be the most you could get. Unfortunately, that is not the case. So what they do is, okay, so 1, 2, 3, 4, 5, yep. They are willing to make an exception so that you can put more carboxylic acids on the chain. But it gets weird, because what they do is they say now the carbon of the carboxylic acid group is no longer part of the chain if you have more than 2. Now, I'm putting an OH on here for a reason we'll get to later. But, so if this guy down here at the bottom, if he weren't there, then this would be a pentane dioic acid, or a 3-hydroxy pentane dioic acid, right? Not a problem. But because we have 3 carboxylic acids on there, and it's not actually possible to have them all on the main chain, if you're including the carboxyl carbons as part of the chain, you remove them from the chain. Okay, so you treat this whole thing, including the carbon, as part of the functional group. Okay, so you can attach that functional group to the main chain, but the carbon is no longer part of the chain. Okay. So now your main chain is only 1, 2, 3 carbons long. If you have more than 2 carboxyl groups you're putting on the main chain. for this one. Okay, so that means that you have 1, 2, 3 carboxylic acids that you're including on the main chain because they're attached, their carbons, the carboxyl carbons, are attached to the main chain. So that makes this a 2-hydroxy propan, because now there's only the 3 carbons in the main chain. You've removed all the carbons from all the carboxyl carbons are no longer being counted. 1, 2, 3 tricarboxylic acid. They want to be able to do that because carboxylic acids are incredibly important in organic and biochemistry. Specifically, this guy right here, the 2-hydroxypropan 1,2,3 tricarboxylic acid, also has a common name. You have absolutely heard of it. That's citric acid. So carboxylic acids are one of those functional groups that shows up all the damn time. You absolutely cannot avoid it. It is vital to just living organisms, and generally speaking, and to organic chemistry functionality. So you're just going to have to accept and get used to the strangeness of carboxylic acids. The strangeness of carboxylic acids, with the ability for the carbon to sometimes be on the main chain and sometimes not, will rear its ugly head again when we get to the amides, and it'll continue to work as we run with the esters as well. So let's run through those rules again. So if there are 1 or 2 carboxyl groups, then just go ahead and treat it like an aldehyde. Okay? I'm assuming it has priority here, which it absolutely, almost definitely, positively does. Okay, so 1 or 2 carboxyls, that's your main chain. Just treat them like an aldehyde. The carbon of the carboxyl group is part of the main chain. So carboxyl. So the carboxyl carbon equals part of main chain. Okay. If you have 3 or more carboxyl carbons or carboxyl groups on the main chain, then you don't treat it like an aldehyde, and the carboxyl carbon is no longer part of the main chain. You have to remove it, okay, for all of them, regardless of where they appear on the chain. So your main chain is going to end up being smaller, but you'll have more of the suffix group present on there. That's why we do this. Okay. All right, so let's go through some examples. All right, now we have something nice and complicated. Here we have a carboxyl carbon, a carboxyl group. So that is going to be our suffix group, which means we're going to start counting at that carbon and work our way left. And we're going to have a number of prefix groups. So here we have a hydroxy. Here we have a chloro. Here we have an amino. I'm sure you can hear my cat crying in the background. She's an old lady. And here we have, remember, it gets treated as separately, a 2-oxopropyl. It's attached to the amino, but it's treated as a separate side chain. It's not part of the same thing as the amino. Okay, separate thing. So that means the overall name of this molecule here is, in alphabetical order, 3-amino, 4-chloro, 2-hydroxy, N 2-oxopropyl, pentanoic acid. So 3 amino, 4 chloral, 2 hydroxy, N 2 oxopropyl, pentanoic acid. All right. Let's go through another example. But don't worry about my cat. She's got plenty of food, plenty of water, clean litter box. Took care of all of that before we started in the hopes of getting her to shut up. It did not work. She's just really old. Thinking about taking her to the vet to see if she's got something seriously wrong or if she's just, crotchety. We'll see. Anyway. Alright, so this one has been constructed specifically so that it's not possible to get all 3 of these guys on the main chain. Okay, no matter what you do, that's just not going to happen here. So, instead, we have to choose the longest chain that contains 2 of them. And that's going to be going from this guy here to this guy here, giving us 2 side chains. Okay, this one is nice and straightforward. That's a methyl. Now, when you have a carboxy group on a side chain, then the carboxyl carbon does not count to the length of the side chain. So there's a carbon here, and there's a carbon here. This is the carboxyl carbon. And so this counts as an entire unit, separate from the rest of the side chain. Okay. So that means that this is another methyl side chain with a carboxy side chain on it, making it a carboxy-methyl side chain. So there's 2 carbons there, only one of them counts to the length of the side chain. Okay. I'm really trying to drive home that when you have a carboxy, or something like that, then it just does not count to the length of the chain. Okay. So 3 or more carboxyl groups, then the carboxyl carbon doesn't count to the length of the chain. If your carboxy group is on a side chain, the carboxyl carbon doesn't count as part of the length of the side chain. Okay. So it's something you're going to have to struggle to remember. Sometimes they count to the length of the chain, sometimes they don't. I'm sorry. So, this one is going to come first alphabetically, then this one. 1, 2, 3, 4, 1, 2, 3, 4. Okay, so we're going to count 1, 2, 3, 4, 5, 6, 7, 8. Making this 4 carboxymethyl, 5 methyl, octane dioic acid. That's another thing that I should have noted. I'm sorry for not pointing it out earlier. Remember this guy. OH, OOH, OOH, OOH. Our citric acid, when you have more than 2, when it's 3 or more, when they're no longer counting to the length of the chain. Okay, this was, this was a 2 hydroxy propane, tricarboxylic acid. So they changed the name that way too. Okay. So that is the way to differentiate between whether the carbons count toward the length of the chain or not. Carboxylic acid, they don't. Oic acid, they do. All right. So next week we will talk about amides, and the week after that we will talk about esters. Amides and esters are ways of making more branching off of carboxylic acids. So you're going to get to deal with that fun stuff as well. They deal with them in different ways than... how best to put this? Esters deal with them of necessity slightly differently than ethers do, but it should be somewhat familiar. Amides deal with branching off of the nitrogen in the same way that amino groups do. So there's not much different there. So hooray for that. Okay, that's it for our carboxylic acids. I'll see you next week for our amides.